Hello, it's me, 3D Caleb again, back to do the final video, going over the rasterizer, and Pete's pretty excited to look at this boring code. He's like drooling. So I'm back to do the rasterizer video because I thought it'd be nice to complete this since I did the ray tracer. So, just get everything wrapped up, and then I will move on because I'm working on new stuff. I'm working on a 3D maze game right now in DOS. It's gonna kind of look like that Windows screensaver maze. Maybe I'll put a little example here in space so you can see it, and you'll go through halls and demonstrate some depth sorting technique. A depth sorting technique, texturing, maybe some lighting. It'd be fun. So I'm working hard on that, and got a lot of stuff left to do, but I've made some good progress on it. And then I got something else cool I'm working on right now as well. I won't share anything about that yet because I want to make sure it actually can kind of get some of it even working. And so I will eventually kind of show that if I have anything that I can actually build and something that actually works, and I'll present it to you and see what you all think. And I think it's a fun project. Okay, anyway, so let's get on to the Rasterizer code and just walk through the C code that I spent some time a few weeks ago cleaning up. So, okay, here we are looking at the monitor, and hope it keeps its red channel active because it keeps going to this nasty bluish tint and it looks bad, but it's okay for now. So this is the Rasterizer C code that I put on my GitHub that you can check out whenever you want. And I tried my best to clean up some of the mess that was in here because I was following the pseudocode in the book, and also use a little guidance from his JavaScript that the author has on his the JavaScript demos that he has on his website. I used some of that as a little bit of guidance when I got stuck on some things. So from the top, we got the basic headers. There's my handy constants. Got pi, got a little depth epsilon value there for getting clean rendering that it will be used. That's used in depth comparison. Helps sharpen that up. The text rendering, actually I don't know why I have that in. I think I was supposed to delete this. I think that's dead code, but oops. Anyway, because I did have a character drawing system, but I removed that to make the code a little more focused. Got my light definitions and my clipping plane count, because we do clipping plane in here, so we can make it a little bit more efficient, but also not break when something's behind the camera. And my swap vectors to help with some of the functions down below. Then my data structures there for doing matrix operations and defining vectors and defining triangle information, then even defining a model that's composed of triangles, vertices, and a bounding radius, and that's used for, like it says right here, that's nice, used for the culling process. And I have an instance, and that which contains the position and orientation of the model that this points to, which is used down lower in the code in the main entry function. There's a plane just defined by just the distance and a normal of where it's pointing, and our camera, and I've defined the clipping planes in there. And of course the camera also has a position and an orientation. And then finally there's our light structure that has its intensity and a direction that it's pointing, of course depending on the type. And then the type is stored here. And then we got global variables for our back buffer and depth buffer. I don't really need to do this because I'm not actually going to be animating where I have to keep flipping the buffer, but I just left it in here as an example to see how you can do a really simple double buffering when you're utilizing mode 13H, because that's extremely easy to draw because you just get that 64,000 kilobyte linear buffer. Here's our prototypes. They're for all sorts of things like initializing our custom palette, initializing our depth buffer, allow us to get the shaded color based off so it allows us to get a shaded color based off an intensity, set our mode, set pixels, clear screen, present the buffer, and is closer pixel, which is used for the Z buffer to determine if the pixel that's almost going to be drawn should be or not. Then our core math operations, like for doing vector addition, division, calculating the length, the dot product, the cross product, helpers to make vectors a lot easier, since the C89 makes things a little bit more challenging to initialize things simply. And then some very important matrix functions, all very simple how they work, but a couple of them have quite a bit of just basic multiplications. And then we have an interpolate, concat, which interpolate function is a very important thing that the author goes over many times in the computer graphics from scratch book. Concat size, draw, fill a triangle. There's this, look at the same functions that are even, I think, defined in the book in pseudocode. Then we have our lighting functions that help with, calculate our lighting, like getting the normal of a triangle, and then the function that's a little bit, this is probably one of the most complicated, I think, in here, is getting the illumination value for a particular pixel on the object as it's about to be finally rendered. Then the pipeline, so our viewport to canvas, projecting the vertex, going from 3D to 2D, and to get it ready to map to this, flat screen. And yeah, rendering model, render the scene, render triangle, and that's it. So then our generation functions, which actually took this one. I was curious how he did this. So he actually did it in JavaScript on his site, on his website, the author, and I just not reversed it, but I translated it from JavaScript into C. And then I made a simple generate plane because I didn't want to use a big sphere for the yellow ground. Because like he was doing it, I want to make it just a bit simpler, and just made a flat plane composed of various triangles to make a terrain that doesn't have any deformation of any kind. Here's our implementation. So there's our in a palette. It's pretty much the same as the one that was in the ray tracer. It sets up our palette because we wanted to find a custom palette, because the default won't work well enough, since we want a lot of different shades for the red, green, blue, yellow spheres. So this is me building the palettes from scratch. They got 64 shades for each color. There's our super simple, this is wonderful, super simple depth swap. Or actually, sorry, initialization. It's amazing. You just use a mem set and clear the whole buffer out to 0. It's awesome how fast and efficient that is. Here's the shade color computation. There's our set mode, how we get things into either text mode or into mode 13H, which of course is also mode X and mode, I don't know, 10? I don't think so, but I know there's mode X, and that uses a planar memory map. It's a little bit different. I think it has a higher resolution but less colors. That's why 13H was so popular, as it had a good amount of colors that you could define in a decent enough resolution, once you account for the squash pixels. There's our is closer pixel function that helps with the Z buffer to figure out if a pixel should be written, or there's one that's already closer than it, so it should just be discarded. Here's our super awesome clear screen. Again, just a mem set with the color. Just, really efficient. And the present buffer, which is also a mem copy, just whatever in the back buffer, just pass it to here, wherever this is pointing to, and that's the starting address of the graphics display, where you can start, changing colors on the screen. So there's our vector addition, vector subtraction, pretty easy stuff. Division, then our length and dot product, and our cross product, which you can find in any linear book, math book, I'm sure. There's our make functions, and here's where there's a lot of those multiplications and additions when you're doing a matrix, multiplying it by a vector, which I guess this is technically a matrix, but just like a 1x4. But this is doing vector multiplication by a matrix. Then we have an identity, which is really important to be able to set up a valid blank matrix with the with a diagonal set up to 1. We have our transpose function, which are pretty simple. They look big, but they're just this really simple multiplication addition. You can get it right from graphics textbooks have these, and I've copied many of these from books. It's like it hasn't changed. I can't wait till I have a good library of my own where I can just always pull my own functions and don't have to keep writing this stuff, because I've done it probably too many times. This is our matrix rotate Y, allows us to build a rotation matrix that is rotated around the y-axis, and we use that to I think I was using that, maybe I don't even know if I use it now anymore, but I was using it to, I think, rotate the camera. I was having some fun with that. And then translate to be able to move, you know, things like the spheres, scale the spheres, and the interpolation for figuring out how to, it helps the triangle drawing figure out the slopes and how, you know, many pixels to fill in between 2 points on a triangle. Here's a draw fill triangle, which this is kind of a tricky function, and I kind of followed more of the author's JavaScript. I wrote my own, but then I went to go look at his, and I sort of like the way he organized his JavaScript triangle drawing method. So I restructured mine a bit to look similar to his, but mine is, of course, a lot more code because I don't have the nice environment like JavaScript gives you, with plenty of awesome, you know, collection helpers. Assignment is easy. I have to be more verbose in C89. And then here's our computer triangle normal, which is really important for the lighting, so we get the right lighting effect. Then here's the illumination, where it goes through all the lights in the scene and the objects to figure out, well, you pass in a vertex, a normal, and the light. Then also the camera's position is even used to figure out the final intensity that should output for a point on, say, a triangle that's being drawn, and how bright it should be, bright or dark. And this code is, I cleaned it up more. It was way messier before, but this was probably the trickier part, is just getting all of this right. And like the point light, which takes into account where the camera is and where it's facing in the scene. The ambient light, of course, is pretty simple. That is always a base value that gets added to the intensity as it begins to loop through all the lights. So there's always a little bit of light on all the objects, so it's not completely black. And then this is how we get things mapped to the canvas, which is screen is our canvas. Then projecting the vertex, so taking a 3D point, getting it projected onto a 2D surface, setting up our, that kind of sets up a transform for us, setting the scale, translation, and this little helper for getting the instances ready. Then the clipped, seeing if any of the objects are outside of one of the clipping planes. If it is, then we'll discard it and not even waste the time trying to rasterize it. And then here's the render triangle, which does the back face calling, which is important. We don't want to, you know, draw things we can't see that are facing away from us, which the dot product helps us determine if a face is facing away from us and, you know, not possible to be seen. Here's where we're computing our lighting, so we're getting our triangle normal. Then we call that compute illumination, which comes back with our intensity. And then we pass that intensity into our shade color to adjust this color, which could be blue, to make it a certain shade of blue based on how it's being lit. And there's our render model that goes through different vertices and triangles, and then to eventually call our render triangle function to do the rest of the work, and trying to free things up, which is always good to do in C. Once you allocate anything on the heap, since it won't be freed up, you got to make sure you clean up. It's on it because, you know, we don't have the luxury of garbage collection like you do in C#. Render scene just goes through all the instances, which in this case would be our spheres. Kind of just broke this up to many smaller methods of how everything gets drawn onto in the world. Here's the generate sphere peak, which is cool how this actually allows you to find how many divisions it should have, you know, how smooth it should be. I have it pretty low. This was a kind of tricky one to write, but I eventually got it functioning, converting it from the JavaScript. And then I have a generate plane, which is a lot simpler, but you can give it a, what is it, like, how many divisions and have the size. Ooh, seeing that? Pretty cool. Then a handy free model function that just goes through all the different fields inside the model structure that have memory pointing to somewhere on the heap that needs to be released. And then finally our main entry point, where we generate our sphere with 13 divisions, generate our plane with 20 divisions, and 30 size, which I don't really know the units, 30 size, 30 units. Instances, this is going to be our spheres and our lights. And here we go, set up our lights. We're going to have 3 lights. We have an ambient, directional, and a point light at different directions and different intensities. And then we set up our instances, which are going to point to a model. So we actually, it's kind of efficient. We're not defining multiple models. We just define one model, and our instances all point to that same memory where the sphere's been set up. It's kind of cool so you're copying it. So we're setting our positions of our spheres and positioning the camera, putting it a little bit back on the Z towards us. It doesn't have a rotation, so it's just looking straight on ahead. Set up our clipping planes, our 5 clipping planes, kind of make a cutoff pyramid. And then we get to initialize our graphics, our depth buffer, clear the screen. That's our background. And then we render. We pass, here's how many objects we need to render, and here's how many lights. And so you can't, I don't know how you in C can get the size of an array if you don't know. I think it has to be known ahead of time. You can't just figure that out like you can in other languages, like say lights dot size or lights dot count. You don't have the luxury of that. So there's a great rundown. It's probably useless rundown of the code, and let's just go ahead and run it because that's more fun than looking at the code here. And ta-da, jang! There's the cool spheres. There's the ground plane. And what's fun is you can change things up a little bit. Like if we go back down and into here, and maybe like the red sphere, we're going to move back even more. Let's move it further. Let's put it like, I don't know, 8 or yeah, like 9. Let's push it. Let's really push it back. Let's go to here. Let's compile it. See what that does. So it's fun to change lights, change where the spheres are. You could even make it so the camera could move too. If you wanted to, you can walk around in this. I don't think the frame rate would be very good. It's not super optimal, but hey, look at that. Now it's far back. So it's fun to do things like that and mess about with the rasterizer, and hopefully this will help you if you follow the book, Computer Graphics from Scratch. This code will help you get through it and write on your own in maybe a very different way. And that is all for the rasterizer. It's done. I feel like I've spent a lot of time on this, and I'm glad to be able to move on now and just we'll focus on the maze game that I'm building. I think that's going to turn out fun or stupid, but it'll be cool to see it. And then my other special project I'll continue working on, and I'll eventually show you that. So check the code out if you want, and hope you have a fun time maybe building this and doing more with it than more than what I'm going to do with it. And I will see you in the future.